Hello everyone, today we're going to learn 4.4 spanning set. Before we do the definition, I want to give you some idea what is spanning set. Okay, so let's think about R2. R2 means two-dimensional space, or we can think that's a plane, right? So any vector in R2 is x, y. We can express by x and y, and we also can express this by I times x times I plus y times j. So you can see for any vector can expressed by I and j. For example, 1, 2 vector, which is I plus 2j. 4, 5 vector, which is 4i plus 4j. So that means any vector can be expressed by I and j. And if we put ij together, so we just say this is a spanning set. Or we say this ij spans R2. Okay, so this kind of a spanning set was the meaning of that one. So now let's take a look at several definitions and then we will do the example. Let's see. The first definition is called linear combination. Linear combination. Let's see. What's the meaning of that one? If we have C1, V1, so you can see C is the scalar, V is the vector, right? And C2, V2, general, C and Vn. This, you can see this is sum of a constant times like a vector. This is called linear combination. Okay, so here vectors are Vi are vectors and Ci are scalars. So here Vi are vectors, Ci are constant or scalars. Same thing. Linear combination. Okay, so let's see. If we look at like a 4i plus 5j, this is linear combination. I and j both are like vectors, right? So linear combination of ij, something like that. Okay, so here I made a mistake here. This should be 5j. Okay, now let's take a look at the second definition. Spanning set definition. So if every vector in a vector space can be written as a linear combination of vectors v1 to vn, then we say v is spanned by those vectors. Let's see. If every vector in a vector space v can be written as linear combination of all the vectors v1 to vn, then we say the v vector space is spanned by all we sometimes call generated by those vectors v1 and vn. Okay, and if we put those vectors together like as a set, this is called a spanning set. For the vector space. Okay, so we also say this set spans V. Same thing, spans and generate means the same thing. So you can keep in mind I, J spans R2, right? The easiest example. And if we look at vector like x, y, j, like this vector, this vector is in R3, three-dimensional vector space, and we can write this as xi, yj, zk, right? And here I is this vector, j, k is this vector. So you can see ijk spans R3, or we can say R3 is spanned by ijk. Because any vector in R3 can be expressed as linear combination of ijk. Okay, so now let's take a look at the first example. Show that R2 is spanned by those vectors. Those vectors are V1, which is 1, 1. V2 is 2, negative 1. Okay, we know R2 is spanned by ij, right? But you know the spanning set is not unique. Sometimes it can also be spanned by or generated by other vectors. Ij is the easiest spanning set, okay? But there's also other spanning set. Let's take a look at this one. R2 is spanned by those two vectors. We want to show that. So let's see how to show that. That means for any vector in R2 can be expressed as a linear combination of V1, V2. So that means linear combination, think about the definition. C1, V1, C2, V2. So that means any vector can be expressed as linear combination. So the meaning, any vector can be expressed as linear combination of V1, V2. So if the C1, C2 exists, we can say that's true. We can say C1, V1, V2 generate R2. Okay, so we just want to see if the C1, C2 exists. Let's simplify this thing. And here we get x, y, which is we combine. We know the scalar multiplication, and we know how to do the addition of two vectors, right? So we just do scalar multiplication and the addition. So the first component becomes C1 plus 2C2. Is that right? And second component of this sum is C1 minus C2. And if we look at this equation on the both sides, so left side equals the right side. So first component equals the first component, second component equals the second component. So here we get two equations. Those two equations, I'm going to write down the two equations. X equals C1 plus 2C2. Y equals C1 minus C2. Okay, and we noticed for any given vector, so x, y should be given. So it's like a constant b. I'm going to rewrite this a little bit, just to change the left side and the right side of the equation. So I'm going to write down like this way. C1 minus C2. They're the same thing, same equation, linear system, right? So you can see here we have linear system with two unknowns. So C1, C2 are unknowns. For any vector x, y, so x, y can be given. I will show you later, okay? C1, C2 are unknowns. So we just want to solve for C1, C2. So here it's like kind of like soft linear system. We can use any method. Do you remember Cramer's rule? I think that's pretty easy. So let's take a look at when the determinant of the coefficient doesn't equal to 0. So we can find the solution. Let's see. A equals what? 1, 2, 1, negative 1. calculate this determinant. -1 minus 2, which is -3, it is not zero. So we say this linear system has unique solution, and the solution is equals to x1 equals what? x2 equals what? Do you remember Cramer's rule? Cramer's rule is determinant of B1. B1 means replace the first column by B. So B are x and y for this case. And second column, same thing. Let's simplify. So negative x minus 2y over -3. Is that correct? You don't have to simplify. And for the x2, which is B2 determinant, what is B2? B2 will replace the second column by B, right? Second column by B. So replaced by x and y should be y minus x over -3. Sorry, it's not x1, x2. It should be c1, c2 because c1, c2 are unknowns. They are the two solutions. So in this case, that means for any x and y, c1, c2 exist. We can find the linear combination. So v1, v2 spans R2. We can write down here, for any vector x and y, we can express this by c1 v1, okay, plus c2 v2, because we already solved for c1, c2, right? For example, for vector, which is 2, 1, that means x is 2, y is 1. We can plug in them into c1, c2. So let's see, c1 equals what? c1 equals negative x minus 2y over -3, plug in. So -2 minus 2 over -3, so it should be 4/3. Simplify, right? And the c2, same thing, plug in. What is c2? Y minus x over -3, so plug in. Y is 1, x is 2, and -3. Because when xy equals 2, 1, that means x is 2, y is 1. We just plug in, and this is -1 over -3, so it should be positive 1/3. So you can see for the vector 2, 1, this equals 4/3 v1 plus 1/3 v2. Right? So actually we can change the x, y into other vectors. For any vector, we can always find the c1, c2 corresponding for the given x and y, given vector. Okay, so it's always can express by v1, v2. So we can say v1, v2 less spans R2. Okay, spans R2. That's the first example. Let's take a look. So we just use the definition. For any vector, first step is very important. For any vector, it can be written as linear combination. We just want to solve, prove, or show if the c1, c2 exist. If x, y can be written as linear combination. Okay. Now let's take a look at example 2. After that, I will give you the exercise. Example 2 is similar. Okay. Determine whether the vectors, so here we have 3 vectors. And v3, 4, -3, 5 span R3. Okay, we just want to see if those 3 vectors span R3. Same thing, do you remember example 1? We, for any vector in, but here in R3, So it has 3 components, x, y, z, right? It's a linear combination of C1, C2 with C1 V1. So I copied the V3, sorry. So this should be C1 V1, which is V1, 1, negative 1, 4. And the C2 V2, negative 2, 1, 3. And the C3 V3, 4, negative 3, 5. And from here, we can set up 3 equations. Okay, so because we already did this in first example, so I'm going to write down this a little bit in an easy way. So with this, the first equation, something equals y, the third equation equals z, and the left side, you can see the first component should be c1 minus 2c2, because the first component like this way and like that way, 4c3, right? Like that way. And then we look at the second component. Okay, second component. The second component gives us the second equation, which is negative c1 plus c2 minus 3c3. Yeah. And the third equation means come from the third component, 4c1 plus 3c2 plus 5c3 equals x, y, z. And then now we just want to see if this linear system has solution or not, right? So how to tell this has solution or not, or how to solve this? For 2 by 2, it's easy to do like a Cramer's rule, right? But for like 3 by 3, if we do Cramer's rule, we have to calculate 4 determinant, and each determinant is 3 by 3. That's not easy. So we want to use Gauss-Jordan elimination. So we want to use Gaussian elimination method. Okay, Gaussian elimination, we want to solve this linear system. What's the meaning of that one? That means augmented matrix, reduce augmented matrix into row echelon. 1, negative 2, 4, last column, they are the B's. So x, y, z. And negative 1, 1, negative 3, 4, 3, 5. Reduce this into row echelon. Okay, row operation is good. We already have leading 1 in the first row. So row 1 and row 2, 0, negative 1, 1, x plus y, right? And then row 1 times negative 4, 0 times negative 4, 4 times negative 4, negative 16, so negative 11. And here should be negative 4, negative 4x plus j. Is that right? Okay. Row echelon, what is the next step? We want to make leading 1 in the second row, so times negative 1 for the whole row. Okay, and we want to use, we can use this to make that 0 times 11 idea, right? 11, and this becomes 0, and this becomes what? 7x plus 11y plus z. Okay, and let's take a look at this linear system. Look at the last row. Last row is kind of like 0 equals 7x plus 11y plus z, right? Because for any vector x, y, z, any vector x, y, z, so x, y, z can be anything. X, y, z is any vector. So it can be non-zero, okay? Can be non-zero, like a number on the right side. So the right side can be non-zero. We can get something when 0 equals 2, something like that. That is impossible. So in this case, this linear system is inconsistent. That means the system has no solution, right? That means the system is inconsistent. Do you still remember we have three cases? For some linear system, it has unique solution. Sometimes there is no solution, inconsistent. Sometimes it has infinity solution. So for our case, because of the last row, there is no solution. Okay, no solution. That means C1, C2 doesn't exist. So that means C1, C2, C3, there's no solution. That means they don't exist. That means V1, V2, V3. This is not spanning set. It's not a spanning set. O doesn't span R3. Okay, so how to tell if spans R2, R3? Just make a linear combination and see if the linear combination has solution or not. Now let's try this exercise problem. Does this set, so we have three vectors, span, does this set span R3? Here's the solution. For any vector in R3, so same thing, we set xyz equals C1 vector, C2 second vector, and C3 like this vector, and we get three equations from here. The first equation, C1 plus 2C2 plus 4C3. Second equation, negative C1 plus 5C2, C3. And C1 plus 3C2 plus C3 equals X3. So you can also do like this way. If the determinant does not equal to 0, there's unique solution. Okay, but if we want to find like a linear combination, what is C1, C2, C3? So we have to solve. Okay, let's just do. You can see we can do several ways for this kind of thing. I like to do Gaussian elimination, so because we don't know the answer, we just want to see if there is a solution or not. Okay, this is a pretty easy one, so reduce to row echelon. 1, 2, 4, x1, 0, 7, 2, 0, 1, negative 3, negative 1 plus. Here's x plus y. Here's x, and this is negative x plus z. And then let's see, I'm going to have the leading one, so permute those two rows. Zero, 1, negative 3, negative x plus z, and 0, 7, 2, x plus y, right? And make the 7 into 0, 1, 2, 4x, 0, 1, negative 3, negative x plus z, and here 0, 0, negative 3 times negative 7 should be 21, and there 23 here. And after simplify this case here, 8x plus y minus 7z after simplify. And we can see actually the determinant of A is, this one has solution, because if we look at the last row, we can divide by 23, right? And we can get z equals something. And you can also look at A determinant. Determinant of A is 23, actually, is not zero. So in this case, we can use Cramer's rule. Oh, we don't have to, I didn't ask you to find the linear combination. We just want to see if this linear system has solution or not. So we can say here, this linear system, the linear system has solution. If we look at the linear system, in our exercise or example, they all means what? So if we look at linear system, that means like a coefficient A, okay, matrix times C. C means C1, C2, C3, and equals for any vector x, y, z. It's kind of like this. We just want to show if this linear system has solution or not. We just want to show this has solution or not, right? So AC equals V. Let's take a look at the theorem here. The theorem 1 says we have V1, V2, and Vk, B vectors in Rn. Then those vectors can span Rn if and only if A is made by V1, V2 till Vn of Vk. So look at our example. So A is made by what? This is V1. This is V2. And this is V3, the vector. Okay. Made by this, and the AC equals V is consistent. That means it has solution for every vector V in Rn. This is just general thing, but when you see the problem, we always just set up the linear system. Okay, you can set up the linear system from definition, linear combination, like the first step, and then do the second step, or you can just set up A C equals V, and what is A? Change the vectors into column, make the column of A, and you can create A. So either way, but they are the same thing. Next example, we are going to take a look at other vector space. So let's take a look at example 3. Example 1 and 2, they are all vector space like R2, R3, right? Next is vector space of matrices. Verify that A1 equals 1, 0, 0, 0, A2, 1, 1, A3, 1, 1, 1, 0, A4. So we have 4 2x2 matrices, and this spans M2R. M2R means all X, like A, B, C, D. All 2x2 matrices in like with real element, right? So that means M2R. Okay, so let's see. Verify this spans that one. So that means what? Definition means for any vector in MR2. MR2 in any vector means what? A, B, C, D. Any vector can be expressed as linear combination of C1v1, C2v2, C3v3, C4v4. Just copy those 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Is that right? Now we want to combine the right side of the equation. So this is addition of 4 matrices, right? And when we combine them, we get a new matrix. So it's going to be like first position is C1 plus C2 plus C3 plus C4. Is that right? And the second position, like here, this position should be C2 plus C3 plus C4. You don't have to write down the step. You can directly write down equations here. Okay, but I just want to show you the steps. And this position is C3 plus C4. This is C4. Is that correct? That means if the left side equals the right side, so we can set up 4 equations. All the components need to equal to each other. So that means C1 plus C2. C4 equals A. And the second component, the rest A12 position equals B. And the C3 plus C4, which is C. And the C4 is D. We just want to solve this linear system. So this is linear system with 4 unknowns. 4 unknowns are C1, C2, C3, C4. We just want to see if this linear system is consistent or not, has solution or not, right? So actually we can solve this easily. This is, it's already like back substitution. Gaussian, this is already row echelon form because has leading 1, leading 1, leading 1, right? This is already row echelon, and C4 is already D. We plug into C3, so the solution is this one. I'm going to just write this a little bit easy. We can solve this easily actually. C4 is D, and the C3 is C minus D, right? C minus C4, C minus D. And the C2, same thing, plug in C2, C3, so it should be B minus C after simplify, and the C1 is A minus B. Okay, so the any matrix A can be written as a linear combination of those matrices C3, A3, and D, A4. Okay, so any matrix can be written as a linear combination. So we say A1, A2, A3, A4 spans M2R. Okay, so interesting, right? M2R is spanned by those 4 matrices, and actually M2R can also spanned by some easy set, like IJ is the easiest spanning set for R2, and the IJK is the easiest set for R3, and the easiest spanning set for M2R is this one, 1 0 0 0 0 1 0 0 0 0 1 0. It's like an IJK, but 0 0 0 1. This, okay, is the most natural spanning set for M2R, because you can see for any matrices 1 2 3 4, we can express this by 1 times 1 0 0, right, and then 2 times 0 1 0 0, and 3 times 0 0 1 0, and 4 0 0 0 1. So any 2 by 2 matrices can be expressed by those 4. So they are the spanning. They can span. They give us the spanning set. Let's see. We cannot finish everything in this section. It's pretty long. Let's continue polynomial kind of spanning set in the next class. What is the spanning set for all polynomials? So we can stop here.